Let's start with chapter 4 of class 12 physics, that is moving charge and magnetism. Okay, moving charges and magnetism. Let's start with the introduction. 4.1 Introduction. Both electricity and magnetism have been known for more than 2000 years. However, it was only about 200 years ago in 1820 that it was realized that they were intimately related. Basically, we know about electricity, magnetism as separate topics for more than 2000 years. Before 2000 years only, we know about magnets, we know about electricity. But now only, like 200 years ago, it is basically not now, 2 centuries ago, in 1820, it was realized that they were actually intimately related together. During a lecture demonstration in the summer of 1820, Danish physicist Hans Christian Ørsted noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass needle. There was a lecture going on in the summer of 1820 where Danish physicist, that is Hans Christian Ørsted, noticed that a current flowing through a wire caused a noticeable deflection in nearby magnetic compass. He investigated this phenomenon. He found that the alignment of the needle is tangential to an imaginary circle which has the straight wire as its center and has its plane perpendicular to the wire. Basically, if this was a wire, if this was a compass, the deflection of the compass was something like this. Was in this direction, which is a, if we observe this deflection, it is somewhat a tangent to the concentric circles where the current carrying conductor is the center. Basically, this is what they're saying in that paragraph. This situation is depicted in figure 4.1. Let's see. There's a figure. The magnetic field due to a straight long current carrying wire. The wire is perpendicular to the plane of paper. A ring of compass needles surrounds the wire. The orientation of the needles is shown when the current emerges out of the plane of the vapor. The current moves into the plane of the vapor. The arrangement of iron fillings around the wire, the darkened ends of the needle, represents north poles. The effect of Earth's magnetic field is neglected. Basically, this dot here, this is actually a plane of paper. Both the cases, this is a sheet of paper. Into the sheet of paper, there is a hole, and through this hole, there is a current wire passing through it. And in this case, it is going into the sheet of the paper where the compass is kept here. So if we see it, it's exactly tangential like this. The alignment of the needle is tangential to the circle, and the north pole is going in an orderly wise from left to right. It is like this. The north pole here, north pole. And in case of this way, where the instead of this, they reverse the direction of current and the current is coming outward. Wait, it seems I have said reverse. This is going inward wait, yes, this is going inward and this is going outward. No, this is coming outward. This is coming outward and this one is inside. Inside. Here, if we see when the current is going inside, when the current is going inside, here as well they are tangential, but the direction of alignment changed. The north is going, instead of like this, the north is going from right to left in this direction. This is clockwise, this is anti-clockwise. Just the arrangement have changed. And in this case, this in the C diagram, there is, instead of a compass here, the current is going outward, and here they have kept numerous iron fillings, amount of iron fillings, and this arrangement is of concentric circles. This is how a bar magnet also shows, arranges the iron fillings. This is indicating that there is a magnetic field. Let's read this one once more. Figure 4.1, the magnetic field due to a straight long current carrying wire. The wire is perpendicular to the plane of paper. A ring of compass needles surrounds the wire. The orientation of needle is shown when the current emerges out of the plane of paper. The current moves into the plane of paper. The arrangement of iron fillings around the wire. The darkened ends of the needle represent north poles. The effect of Earth's magnetic field here is neglected. The Earth also has a magnetic field, so it will not let the compass here to be exactly in the same alignment. There will be some little differences that is due to Earth's magnetic field, but that is neglected here. That is why we got the perfect result of tangential circles. Okay, let's read from start. Both electricity and magnetism have been known for more than 2000 years. However, it was only about 200 years ago, in 1820, that it was realized that they were intimately related. During a lecture demonstration in the summer of 1820, Danish physicist Hans Christian Ørsted noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass needle. He investigated this phenomenon. He found that the alignment of the needle is tangential to an imaginary circle which has the straight wire as its center and has its plane perpendicular to the wire. Okay, that is what I read before as well. The situation we saw there, where the alignment of the compass and the fillings in concentric circle, it is noticeable when the current is large and the needle is sufficiently close to the wire so that the Earth's magnetic field may be ignored. The current passing, basically this line indicates that the higher the current, the higher the magnetic field produced. This is one of the relations. The magnetic field, or the higher the current passing, the higher the magnetic field produced, directly proportional. And one more is distance. The closer the compass needle is to the wire, the higher the deflection shown. Magnetic field is inversely proportional to distance square. Higher the distance, lower the magnetic field effect. And then one more thing, reversing the direction of the current reverses the orientation of the needle. The deflection increases on increasing the current or bringing the needle closer to the wire. These are the two important proportionality points, where increasing the current, the deflection on the compass, basically the magnetic field, increases when there is increase in current or when we bring the needle closer to the wire. Iron fillings sprinkled around the wire arrange themselves in concentric circle with the wire as the center. Ørsted concluded that moving charges or currents produce a magnetic field in the surrounding space. Based on all these observations, he concluded that currents or moving charges produce a magnetic field. Following this, there was an intense experimentation. In 1864, the laws obeyed by electricity and magnetism were unified and formulated by James Maxwell, who then realized that light was electromagnetic waves. Radio waves were discovered by Hertz and produced by J.C. Bose and G. Marconi. By the end of 19th century, a remarkable scientist, a remarkable scientific and technological progress took place in the 20th century. This was due to our increased understanding of electromagnetism and the invention of devices for production, amplification, transmission, and detection of electromagnetic waves. Basically, what this paragraph is saying this after Oersted gave his conclusion in after he found out this phenomena, he concluded that moving charges or currents produced a magnetic field in the surrounding space. After this conclusion of Oersted, there was intense experimentation. The first thing they gave is in 1864, the laws obeyed by electricity and magnetism, they both were unified and formulated by James Maxwell. He unified the electricity and magnetism laws and formulated them, and he also realized that the light was electromagnetic waves. Then after James Maxwell, radio waves were discovered by Hertz, and they were discovered by Hertz but were produced by J.C. Bose and G. Marconi. That is by the end of the 19th century, 1800s. A remarkable scientific and technological progress took place in the 20th century, that is the 1900s, and this was due to our increased understanding of electromagnetism and invention of devices for production, amplification, transmission, and detection of electromagnetic waves. In this chapter, we will see how magnetic field exerts force on moving charged particles like electrons, protons, and current carrying wires. We shall also learn how current produce magnetic fields. We shall see how particles can be accelerated to very high energies in a cyclotron. We shall study how currents and voltages are detected by a galvanometer. In this and subsequent chapter on magnetism, the next chapter basically, that is magnetism and matter, we adopt the following convention. The conventions are given here for both the chapters. A current or a field, electric or magnetic field, emerging out of the plane of the paper is depicted by a dot. A current or a field going into the plane of the paper is depicted by a cross. Basically, here in these two figures, if we see, here it is going out of the paper, it's coming out of the paper, so it's a dot. In case of here, it is the current is going inside the paper, so a cross. They gave some information about Hans Christian Oersted. Basically, I will read it out. 1777 to 1851, Hans Christian Oersted, Danish physicist and chemist. He observed that a compass needle suffers a deflection when placed near a wire carrying an electric current. This discovery gave the first empirical evidence of a connection between electric and magnetic phenomena. Okay, that was all about him. Now let's go to the next topic, the next main topic, that is magnetic force. The first subtopic under the main topic of magnetic force is sources and fields. Sources and fields of magnetic force. Before we introduce the concept of magnetic field, that is represented by or denoted by capital B, we shall recapitulate what we have learned in chapter 1 about the electric field represented by E. We have seen that the interaction between two charges can be considered in two stages. The charge Q, the source of the field, produces an electric field E. E equals Q r vector by 4 pi epsilon naught r square, where r cap is a unit vector along r and the field E is a vector field. A charge Q interacts with this field and experiences a force given by force equals Q times E, or QQ by 4 pi epsilon naught r square along with a unit vector. Okay, let's understand. They give one more point. A dot appears. This is not relevant to here, but I will just read it in just in case. A dot appears like the tip of an arrow pointed at you. A cross like the feathered tail of an arrow moving toward you. Basically, why they represented dot as coming out of the plane and a cross as going into the plane, because the arrow points the direction of the current, electric field or magnetic field. Basically, they imagined an arrow that is something like this, and if you see this arrow, at the tip, it will be a point like this when you point the arrow towards you. But when you see this from behind, you will see a feathery cross. That is the reason they denoted dot and x as the directions. Okay, let's continue about the sources and fields. We have seen the interaction between two charges can be considered in two stages. The charge, which is the source of the field, produces an electric field, where this is a formula for the electric field, where it is acting towards the direction, the r vector is in the direction of the r vector, and this field is a vector field. A charge q, when we bring in a charge q, charge small q, which is in the presence of the electric field created by the capital Q, this small q interacts with this field and experiences a force F, that is given by F equals q times E. As pointed out in chapter 1, the field is not just an artifact but has a physical role. Okay, it can convey energy and momentum and is not established instantaneously but takes finite time to propagate. Basically, the field E, this can convey energy and momentum, and this is not very instantaneously. It happens slowly with finite time required. That is the reason when we place charges in an electric field, the charges get accelerated. This means the charges are getting momentum, they're gaining energy, that is due to the electric field accelerating them. But this does not happen instantaneously but takes some time to happen. The concept of a field was specially stressed by Faraday and was incorporated by Maxwell in his unification of electricity and magnetism. This concept of a field, this was stressed by Faraday, and this was also incorporated by Maxwell, that is in his unification of electricity and magnetism. In addition to depending on each point in space, it can also vary with time, that is a function of time. Field does not depend only on the each point in space, where each point in space the position vector will denote the amount of field, but it also varies with time, as a charge q not placed in a field Let's assume an electric field for 2 seconds will experience less acceleration than another charge q naught, same magnitude, placed in the same field but for 5 or 10 seconds. The momentum and acceleration will be different in both of the cases. That is what they mean by it can be a function of time. In our discussions in this chapter, we will assume that the fields do not change with time, even though it is a function of time. We assume that it will not change with time. The field will be constant, uniform. The field at a particular point can be due to one or more charges. If there are more charges, the fields add vectorially. Now, if we consider in a real life situation, there is not only one charge isolated, so the field is at a single point that can be due to one or more charges. If there are more charges, then the superposition, which we add up all the electric fields individually, that is vectorially, as their vectors. You have already learned in chapter 1 that this is called the principle of superposition. Once the field is known, the force on a test charge is given by equation 4.2, that is this equation. Force equals QE, or capital Q times Q by 4 pi epsilon naught r square with the r cap. If we know the field, we can multiply it with the charge and you will get the force. Just as static charges produces an electric field, the currents or moving charges produce in addition a magnetic field. Just as how we know that static charges, the region surrounded by a charge, will have an electric field. When the charge is actually moving, it will produce a magnetic field. This is denoted by capital B. Again, a vector field. This is also a vector quantity. It has several basic properties identical to the electric field. Many properties of the magnetic field are identical to the electric field. It is defined at each point in space and can in addition depend on time, that is a function of time. Experimentally, it is found to obey the principle of superposition. The magnetic field of several sources is a vector addition of magnetic field of each individual source. When there are several kind of magnetic fields, if you want to find the magnetic total net magnetic field at a certain point, it will obey the superposition principle. Basically, we find all the individual magnetic fields and add them vectorially. This will give us the net magnetic field. This has been proven experimentally. Now let's go to, actually they gave something about Hendrik Antoon Lorentz. Let's just read it. Hendrik Anton Lorentz, 1853 to 1928, Dutch theoretical physicist, professor at Leiden. He investigated the relationship between electricity, magnetism, and mechanics. In order to explain the observed effect of magnetic fields on emitters of light, his Zeeman effect, he postulated the existence of electric charges in an atom, for which he was awarded the Nobel Prize in 1902. He derived a set of transformation equations known after him as Lorentz transformation equations by some tangled mathematical arguments, but he was not aware that these equations hinge on new concept of space and time. Basically, he observed effect of magnetic fields on emitters of light, and he postulated that there must be electric charges in the atom. Okay, let's start with magnetic field and Lorentz force. Let us suppose that there is a point charge q moving with velocity v and located at r at a given time t. In presence both the electric field E and the magnetic field B. The force on electric charge due to both of them can be written as force equals Q times E plus V times B, which is equals to F electric plus F magnetic. Basically, if there is a point in space, there is both an electric field and a magnetic field. We add the force, the total force on the electric charge due to both of them can be written as the addition of the F electric plus the force of electric force and magnetic force. Lorentz force is basically Lorentz force on a particle, not particle but a charge in space, which is equals to F electric force due to electric force plus F magnetic force, the force due to magnetic field, which is force due to electric is Q times E, plus force magnetic force, it is QEB, which we'll see later. Now we can write this vectorially as QEB sine theta, actually this one, and we can write this as, we can take Q common, E vector plus V cross B vector. This is the Lorentz force. This is a final equation. That is what they said here as well, where they took E of R, basically this is indicating the direction of the electric field, E of R and P of R, which is in the R cap direction. This force was first given by Hans and Toon Lorentz, or H.A. Lorentz, based on the extensive experiment of Ampere and the others. It is called the Lorentz force. You have already studied in detail the force due to electric field. If we look at the interaction with the magnetic field, we find that the following features. Okay, this force was first given by Lorentz, that is based on extensive experiments by experimentation of Ampere and other scientists. This is called as the Lorentz force. You have already studied about in detail due to the force of electric field. Now if we look at the interaction with magnetic field, we find the following features. The force due to magnetic field, the interaction, we find following features, that is this force, it depends on charge, velocity of the moving charge, B, that is magnetic field, that is charge of particle, velocity and magnetic field. Force on a negative charge is opposite to that of a positive charge. If there is a negative charge, it will be opposite of the positive charge. The magnetic force Q times V cross B includes a vector product of velocity and magnetic field, or we can say it as QVB sine theta. The vector product makes the force due to magnetic field vanish, become zero if the velocity and magnetic field are parallel or anti-parallel. Basically, if it is, we know that vector product is QEB sine theta, and when it is sine is theta equals 0 or theta equals 180 degree. In both these cases, the angle if the angle between velocity and the magnetic field is 0 or 180 degree, that is parallel or anti-parallel, then there will be no effect on the particle due to magnetic field. There will be no force. The force acts in a sideways direction perpendicular to both the velocity and magnetic field. Its direction is given by the screw rule or right hand rule for vector or cross product, as illustrated in figure 4.2. Let's see the figure. The direction of the magnetic field force acting on a charged particle. The diagram A, the force on a positively charged particle with velocity v and making an angle theta with the magnetic field B is given by the right hand rule, and B, a moving charge particle Q is deflected in opposite sense to minus Q, the presence of a magnetic field. Okay, the first diagram is, this is a moving charge. This is a diagram here. This is a charge plus Q, and it is, this is the theta, this is the angle between the velocity, and this is the direction of the magnetic field. This is the direction of velocity. The angle between them is represented as theta. Then if we take the vector cross product rule, that is QVB, so we take it to be from V to B, so the force will be acting perpendicular to both of them, that is in this direction. The force will be acting upward when there is a theta angle between B and V. Both are assuming to be in a plane, assumed to be in a plane. Now let's see the second diagram. This is a magnetic field B. There are two charges placed here, minus Q and plus Q here. In the same kind of magnetic field, the force acting on the plus charge is in this direction, whereas the force acting on the negative charge is in this direction. As we saw, there was a statement here that when there is a negative charge, the direction of the force will be reversed. That is what they're showing here. Okay. Third point, the magnetic force is zero if charge is not moving, as the magnitude of velocity is zero. Only a moving charge bears the magnetic force. Let's read the postulates again, or the features again. This magnetic force on a particle, they are talking about the features of the magnetic force or the interaction of the particle with the magnetic field. The main points, features, that is this magnetic force and magnetic field interaction, this depends on the charge, velocity and magnetic field of the experienced by the particle, and this force on a negative charge is opposite to that on a positive charge, that is vectorially in direction wise. The magnetic force Q times V cross B includes the vector product of velocity and magnetic field. So the vector product makes the force due to magnetic field become zero if velocity and magnetic field are having a theta angle between them as zero, that is parallel or anti-parallel 180 degree, and this force acts in a sideways direction perpendicular to both the velocity and magnetic field. That is what they showed here. It is acting perpendicular to both velocity and magnetic field. Its direction is given by the right hand rule of vector or screw rule. And the third feature is, when the magnetic force is zero, the magnetic force is always zero if the charge is not moving. If it's a static force, not static force, if it's a static charge, then the velocity, magnitude of velocity will be zero, and the direction as well zero. There is no direction because it's not moving at all. The velocity is zero. So then QEB sine theta, force, magnetic equals QEB sine theta. If this becomes zero, F magnetic will also be zero. A static charge does not experience magnetic field or magnetic force. The expression for magnetic force helps us to define a unit of magnetic field. This expression of QEB sine theta of magnetic force helps us define the unit of the magnetic field. If one takes Q, the charge, force and velocity all to be in unity in the force equation, F equals QVB or QVB sine theta, end cap, where theta is the angle between V and B, the magnitude of magnetic field is 1 SI unit when the force acting on a unit charge 1 coulomb moving perpendicular to B, the speed of 1 meter per second, is 1 Newton. Okay, this is what we are saying is force equals QEB sine theta. If we take Q equals 1 coulomb, V equals 1 meter per second, then we can define then the magnetic field unit, then the unit of magnetic field is when 1 coulomb of charge moving with 1 meter per second velocity experiences a force of 1 Newton, that is perpendicular to the directions of both velocity and magnetic field. This is basically defining 1 unit of magnetic field. 1 unit is defined, or we can say it is defined as a unit of magnetic field. A unit of magnetic field is defined when 1 coulomb charge moving with a velocity of 1 meter per second experiences a force of 1 Newton. This is defined as a unit of magnetic field. That is what they said here. And as taking all of them in unity means taking charge as 1 coulomb and velocity as 1 meter per second. That is what they mean by that. Dimensionally, we have the magnitude of B, which is equals to force by QV, basically shifting QV to the denominator, and the unit of B are Newton per second, Newton second per coulomb meter. This unit was called as a Tesla, named after Nikola Tesla, 1856 to 1943. Tesla is a rather large unit. A smaller unit, non-SI, called Gauss, 10 power minus 4 Tesla, is often used. The Earth's magnetic field is about 3.6 into 10 power minus 3.6 into 10 power minus 5 Tesla, or rather 3.6 into 10 power minus 1 Gauss. Okay, dimensionally we can derive this equation. Dimensionally, if we can get force by QV is equals to magnetic field as from equation F equals QVB. When we shift QV denominator, we'll get dimensionally this equation, and unit of or SI unit of magnetic field B is Tesla. We can define a Tesla as when a 1 coulomb charge moving with a 1 meter per second velocity experiences a force of 1 Newton due to the magnetic field acting in a direction perpendicular to both the velocity and magnetic field. And in this is in SI system, in CGS system, the unit of magnetic field is Gauss, represented by G. Here it is T, where T equals 10 power 4 Gauss, or 1 Gauss equals 10 power minus 4 Tesla. And the Earth magnetic field is about 3.6 into 10 power minus 5 Tesla, or 3.6 into 10 power minus 1 Gauss. And the next topic is magnetic force on a current carrying conductor. We can extend the analysis for force due to magnetic field on a single moving charge to a straight rod carrying current. Consider a rod of uniform cross-sectional area A and length. Okay, the charge carriers are in a conductor are only electrons. Let the number density of these mobile charger carriers be n, small n, the total number of electrons in the conductor to be n, the total number of mobile charge carriers in it is NLA. Okay, this n is not the total number of charge, but the n is number of electrons in a unit volume of conductor. So when we multiply n times L into A, where L into A is the volume of the conductor, where n times V is equals to n times A into L is equals to the total number of electrons in that conductor. For a steady conductor current I in this conducting rod, we may assume that each mobile carrier has an average drift velocity Vd, mobile carrier meaning electron. Vd is the drift velocity. In the presence of an external magnetic field, the force on these carriers is NLA times Q times Vd, which is the drift velocity, times B, or cross product with B, where Q is the value of charge on a carrier. Now N times Q times Vd is the current density J. And when we multiply this with area is the current I. And we can write this as J times AL times B, or simply ILP. Okay, let's derive it ourselves. Let's assume this is a conductor. This is a conductor where, let's assume the electric field acting in this direction. Electric field is in this direction. These are the electrons moving in this direction with a drift velocity Vd. Now there is also a magnetic field acting on this conductor. They are not give theta in some angle, it's acting on this conductor. Okay, we know the formula F magnetic, which is equals to QVB sine theta, or QV cross B, and the total charge here is, let's assume N is the number of electrons, unit volume, N times L into A, where the length is L and area is A, which is total number of electrons in a conductor, in this conductor actually. So the total charge will be Fm, which is equals to NLA times Q, and V is the drift velocity cross B magnetic field, and we can write this again in another way as Vd Q times Na is equals to length times magnetic field, is one way of writing it. And we know I equals from chapter 3, I equals Vd ENA, where E is the charge of the electron. Here as well you can write this, instead of Q we can write this as E, as we are taking individual mobile carriers that are electrons, mobile charge carriers. Vd ENA, so substitute I in this place. So force on a conductor, which is equals to I L times B ILB sine theta, basically ILB, where sine theta is the angle between the conductor and the magnetic field, I believe. And another way of writing is in terms of the current density, where we can write I times where I by A equals current density J. We can write J times A, which is equals to I. Substituting it, we will get magnetic force, which is equals to current density times A times L cross B. But mostly this equation is the final answer. Now let's continue. So finally I L cross B, where we can write as ILB sine theta, where L is a vector of magnitude L, the length of the rod, and with a direction identical to the current. The direction is same as the direction of current. Note that the current is not a vector. In the last step leading to equation 4.4, we have transferred the vector sign from the current density to L. Equation 4.4 holds for a straight rod. In this equation, B is the external magnetic field. It is not the field produced by a current carrying rod. If the wire has an arbitrary shape, we can calculate the Lorentz force on it by considering a collection of linear stripes dl and summing the individual currents. And okay, basically what they're saying here is the first information they said is L is a vector of magnitude L, that is the length of the rod, and its direction is the identical, it's the same as the direction of current. Here current is not a vector, and this equation is only true for a straight current carrying conductor, and here we have not considered, since there is a current carrying conductor, the moving current, the moving charges, the moving electrons will also produce a magnetic field. This is not considered here. We are only considering when a current carrying conductor is in the presence of an external magnetic field, then the force experienced by that conductor is ILB, and here L is a vector and B is a vector, and we can write it as ILV sine theta. Theta is the angle between the magnetic field and the length vector. And when if the field is, if the wire, like we consider it is in a straight rod or a straight wire, but if the wire is not straight and it is in a arbitrary shape or any kind of weird curved shape, then we can calculate the magnetic force, or here Lorentz force, they are talking about both electric field and magnetic field. But if you want to calculate the magnetic field alone, then we consider this, if there is a wire of shape like this is the current, then we consider it as linear dl tangential strips like this. We consider it like that, and we take the summation F magnetic equals summation of, I think they gave J here, I, right, J IDLJ times B vector. This is current, this is the total individual currents with the total summation of the individual length vectors with individual directions, or I mean individual angles between the B vector and the length vector. This summation can be converted into an integral. In most cases we can write it as with limits, integrals with limits. Now let's see the example given here. An example 4.1, a straight wire of mass 200 grams and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of the magnetic field? They gave that information. Given here is a straight wire of mass 200 grams, possibly given because of the gravity, force due to gravity, for us to calculate the force due to gravity. And they gave the length of the rod, which is around 1.5 meter, and it has a current of 2 ampere. This is suspended in mid-air by a uniform horizontal magnetic field. They're asking that it is suspended in midair. There is no wire hold, there is no kind of rope holding this straight wire of mass 200 grams. It is suspended in midair, it is floating in the midair. That is due to the magnetic field. From equation 4.4 ILB sine theta, we can find that there is an upward force F of magnitude ILB for mid-air suspension. This must be balanced by the force due to gravity. Just a minute. Okay, since it is balanced like that, sine 90 degrees is 1, it is horizontal, the length vector and magnetic field is perpendicular to each other, I guess. Okay, then ILB, so mg, which is the gravitational force, must be equal to the force experienced by the conductor, that is ILB. That is because it is floating in the air. That must mean it is balanced by the force due to gravity. So mg equals ILB, B equals mg by IL, which we know that mass equals 0.2 kg or 200 grams converted into kgs. The acceleration due to gravity is 9.8 meter per second square. The length of the rod is given as 1.5 meter. Current flowing through the conductor is 2 ampere. If we calculate this, the final magnetic force is 0.65 Tesla. Note that it would have been sufficient to specify mass times length. The mass per length of the wire, the Earth's magnetic field, is approximately 4 into 10 power minus 5 Tesla, and we have ignored it. It's a very minute magnetic field, so we have ignored this. Instead of taking this, we can represent it as unit length as well. Instead of taking exact length of the wire, we can just state it as 0.65 per length of wire or unit length of wire. Okay, let's go to the next example here. Example 4.2. If a magnetic field is parallel to the positive y-axis, okay, and the charged particle is moving along the positive x-axis, which way would the Lorentz force be for A, an electron, negative charge, and B, a proton, a positive charge? Okay, this is the three-dimensional view here. These are the x, y, and z axes. The magnetic field lines are this way in the positive x direction. If that was the case, in the case of the z axis, in case of z axis where a magnetic field is like this, what will be the direction of the force on an electron and a proton? So normally it is QVB, so it is from velocity to direction of magnetic field. The charged particle is moving along the x-axis here, x and z. The particle is moving in this direction. We take that, then both are perpendicular, and when we take the direction, it will be acting towards the z-axis, that is for a proton. If it was an electron, it will be acting opposite to that will be negative z-axis, that is the direction of the Lorentz force. The velocity of a particle is along the x-axis, while The magnetic field is along the y-axis, so V cross B is along the z-axis, right-hand thumb rule. So for electron, it will be along the negative z-axis, as I told. For a proton, the force will be along the positive z-axis. Now let's go to the next main topic, that is motion in a magnetic field. Motion in a magnetic field. We will now consider in a greater detail the motion of a charge moving in a magnetic field. We have learned in mechanics that a force on a particle does work if the force has a component along the direction of motion of the particle. In the case of motion of a charge in a magnetic field, the magnetic force is perpendicular to the velocity of the particle, so no work is done and no charge. The magnitude of velocity is produced, though the direction of momentum may be changed. Notice that this is unlike the force due to an electric field, QE, which can have a component parallel or anti-parallel to motion and thus can transfer energy in addition to momentum. Basically, they're saying that in case of a magnetic field, we saw in mechanics that not in case of, like normally where a force will only do work done. Let's assume this one. Let's assume work done equals F times F dot D or FD cos theta. FD cos theta. So when theta is 90 degrees, work done will be 0. In this case, in case of a magnetic field, it is in case of a particle, q will be sine theta. Theta, if it is, theta should not be equal to 0 and 180 degrees. If so, then force will also be not equal to 0. When theta equals not equal 0 and 180 degree, force will also be not equal to 0. Let's assume that theta is 90 degrees. Theta equals 90 degrees, where force M, which is maximum, and it only works in the sine theta direction, sine theta component. In this case, this magnetic force, we know that, let's take in case of mechanics example, this is a block of mass M, this is a rod or something like that. If in this case, let's assume we apply a force like this, which is perpendicular yes, which is, let's assume the velocity is moving, the velocity of this particle is in this direction, this box is moving in this direction, and if we apply a force perpendicular to the velocity, then work done, there is no effect on the motion of the box. That is in a very ideal world, where we saw force equals, work done equals ft cos theta. When theta equals 90 degree, this will become 0 when theta equals 90 degree, so work done will be 0. And we saw that the force, magnetic force, acts only in the sine theta component, or in this case we can write the sine theta, the sine component of force does no work. Let's just verify that once. Does the sine component of work, no wait, of force angle between velocity and force does no work. Yes, that is indeed the case. So when we take the sine component of force, it does no work. But in case of magnetic field, if we see, in magnetic field, the magnetic force is only applicable in the or sine direction or sine component, or for the sine component for the sine component of velocity, where it should, if that is the case, when we observe this both statement, the sine component of work does no work, and in magnitude the magnetic force is only applicable for sine component. This is the angle between velocity and magnetic field, and the force is only in the sine direction or 90-degree perpendicular. So in such a case, only sine component we take it. So we can conclude that conclusion: the work done due to magnetic field will be zero, and as such there will be no amplification in magnitude of momentum of body, but only a change in direction. There will be no acceleration of the body, there is no increase in momentum of body for a particle moving in a magnetic field. There will be no amplification in magnitude of momentum, there will only be a change in direction. It will not slow down the particle, it will not speed up the particle, but it will only shift the path of the particle or the charge. That is what they're saying in the paragraph in NCERT. Just in case, I'll ask, is the work done due to magnetic field or magnetic field, but magnetic force always zero? Yes, the work done by magnetic force will always be zero. The magnetic force does no work because it always perpendicular to the motion of the charge. It is always perpendicular to the motion of the charge. In such a case, it will do no work. It just changes the direction of velocity, but not its magnitude. Speed or kinetic energy remains constant. There is only change in direction. Speed will remain constant, but velocity, as it is a vector, will continue changing due to direction. That is what they're saying here. The motion of a charge moving in a magnetic field, we have learned in mechanics that a force on a particle does work if the force has a component along the direction of motion of the particle. If only if the force is along the direction of motion of the particle, like velocity, and there is a cos component, then only there will be a work done. The magnetic force is a perpendicular to the velocity of the particle, so no work is done and no change in magnitude of velocity is produced, though the direction of momentum may be changed. Notice that this is unlike the force due to an electric field QE, which can have a component parallel or anti-parallel to a motion and thus can transfer energy in addition to momentum. As we see, when we place a charged particle in an electric field, there will be an acceleration of the particle. The particle will accelerate, will get accelerated, will gain energy. There is a point I discussed at the start. But in case of magnetic field, there is no such thing, as there is no force component acting parallel to the direction of velocity. In magnetic force will never do work done, will never do work. We shall consider motion of a charged particle that is in a uniform magnetic field. First, consider the case of a velocity perpendicular to the direction of magnetic field, where the sine theta is sine 90 degree. The perpendicular force QVB acts as a centripetal force and produces circular motion perpendicular to the magnetic field. The particle will describe a circle if V and B are perpendicular to each other. Okay, as we can go into greater detail here, let's change the pen. Let's assume there is a magnetic field going into the board or into the screen like this. Let's assume it is everywhere. I won't be drawing it, but let's assume it is everywhere. This is the magnetic field, and there is a positively charged particle plus q with a velocity of v and this direction. And if we see through planes, then the angle between velocity and magnetic field theta will be equal to 90 degree. So the force in, let's assume instant t equals 1 second or so, like in this instant, if we calculate the direction of the force, it will be, if we calculate, it will be according to the thumb rule, it will be, let's assume it's acting out, no, it will be acting this direction. This is the force, this is the direction of force. It will be perpendicular to the velocity component, so the particle will go in this direction. It will move in this direction and there will be a change in velocity. This is, let's assume t equals t1, or let's, in reference, let's take 1, t equals 1. Now let's assume there is second case, the same magnetic field, the particle change its direction of velocity like this. From here to, it shifted like this because the force was acting in this direction. Now if we see the angle between velocity and magnetic field, it will now also, it will be 90 degree, but the direction of force will change. Now in this case, where the velocity of is this side, the force will be acting this side. Now again, this is in, let's assume t equals 2 second or something like that. Now in case of t equals 3 second, the velocity of the particle will be in this direction because the force was acting in this direction. Now again, if we calculate the direction of force due to this direction of velocity and magnetic field, then the force will be acting in this direction. Now this is the third instant. Now let's go to t equals 4. Now in this case, let's assume due to the force, the particle has changed its direction of velocity to be this side. Then again the force will be acting towards this side. This will be a cycle where it will be again going to this forward, this t equals 1 instant, where the force will be acting this side, velocity will be this side. And I have only considered 4 positions here, but for every small change in direction of velocity due to the force, there will always be a change in force. Due to that, the particle finally, the final and total path followed by the particle slash charge, or only charge, bracket charge, when angle between velocity and magnetic field is 90 degree, is, let's assume the same diagram, but I'm giving all the 4 instants together, plus q, 4 positions here, where in all these positions, every point of the circumference of this circle, there will be a force direction which will be inwards. Due to this inward force, that is called the centripetal force, it generates a circular motion. There is a magnetic force acting always towards the center. Due to this force acting towards the center, there will be a generation of the circular motion. Here in this case, the direction of velocity will always be changing. In case any point of the circumference, there will be a charge that is moving like this, and in this case, if you want to find the velocity direction, we take a tangent. This is the motion of a particle under where the direction of velocity and magnetic field are perpendicular. The motion of the particle, or the trajectory or path followed by the particle or charge, will be circular motion, where it will be in uniform speed but ever changing velocity direction, ever changing velocity, as it depends on or due to continuous change in direction. Due to continuous change in direction. Okay, let's go to the textbook now. I'll read the paragraph again. The motion of a charge moving in a magnetic field. We have learned in mechanics that a force on a particle does work if the force has a component along or opposite to the direction of motion of the particle. In case of motion or a charge in a magnetic field, the force is perpendicular to the velocity of the particle, so there is no work is done and no change in magnitude of the velocity is produced, though the direction of momentum may be changed. Notice that is unlike the force due to an electric field, QE, with the force of the electric field, which can have a component parallel or anti-parallel to motion and thus can transfer energy in addition to momentum. We shall consider motion of a charged particle that is in a uniform magnetic field. First, consider the case of velocity perpendicular to the magnetic field B. The perpendicular force QAB acts as a centripetal force and produces a a circular motion perpendicular to the magnetic field. The particle will describe a circle if V and B are perpendicular to each other If velocity as a component along the magnetic field, this component remains unchanged as the motion along the magnetic field will not be affected as the magnetic field. The motion in a plane perpendicular to B is therefore a circular one, thereby producing a helical motion. Okay, that is the first case where theta is 45 degrees. I mean, not 45 degrees, 90 degrees. If case 2, theta which is greater than 0, lesser than 90 degree, that is the case. Let's assume this is the magnetic field, or they showed a diagram, I think. Okay, let's assume this is the direction of magnetic field direction. Now let's assume there is a positively charged particle plus q. It is having a velocity v, where the angle between velocity and b is theta. In this case, the velocity can be configured into two components, or resoluted into two components, that is v sine theta and v cos theta, where v sine theta is perpendicular to the magnetic field. Due to v sine theta component, the particle will undergo circular motion, but due to v cos theta component, v cos theta remains unchanged. So the due to the mixture of both circular motion and linear motion, there will be a creation of a helical path like this. That is the case 2, where angle is theta, where the distance between the two circle is pitch, and they'll have a uniform radius, where velocity is resoluted into the v sine theta component, which is the cause of the magnetic force and change in momentum, and the v cos theta component, which is not affected by the magnetic force. As such, it will remain unchanged. I've already learned in earlier classes that if r is the radius of a circular path of a particle, then a force of mv square by r acts perpendicular to the path towards the center of the circle and is called the centripetal force. If velocity v is perpendicular to the magnetic field B, the magnetic force is perpendicular to both v and b and acts like a centripetal force. It has a magnitude qvb. Equating two expressions for the centripetal force, we will get mv square by r, which is equal to qvb, which gives r equals mv by qb. Basically, from this they are deriving there is a centripetal force. Centripetal force is acting towards the center. That is the reason there is a creation of the circular path, and this centripetal force, which is equals to, we have learned that it is equals to mv square by r, where r is the radius. This is the equation for centripetal force, and we know that this force is same as the F centripetal is F magnetic force. So F centripetal will be equal to F magnetic force. I'll derive this down. So we can get F centripetal, which is equal to F magnetic, if in case of the theta equals 90 degree. In this case, mv square by r, which is equals to qvb, where sine 90 is 1. Then we will get, if you want to find the radius, we will get radius equals mv square by qvb, where velocity and velocity square get cancelled, r equals mv by qb. In case where it is a pure circular motion, theta equals 90 degree. In case of the second case where we took a helical path, case 2, just very simple, we take mv square by r, or instead of that I believe we can write it as v cos theta here, v sin theta here, where theta is not equal to 90 degree. So I'll not be deriving that right now. Or yes, that is the case. In case 2 it will be mv cos theta, not cos theta, sin theta whole square by r, which is equals to mv sin theta, not mv sin theta, qvv sin theta, where r equals mv sin theta whole square by qvb sin theta. Sin theta we get cancelled, square get cancelled. So radius in case of helical path will be mass equals v sin theta by qb. Okay, let's continue. For the radius of the circle described by the charged particle, the larger the momentum, the larger is the radius, and the bigger the circle described. If omega is the angular frequency, then v equals omega r. So omega equals 2 pi v, c equals to q b by mass of particle. Basically here if we see radius is directly proportional to velocity and is inversely proportional to magnetic field and the charge. Higher the charge, more the magnetic force, smaller the radius. Or we can say we can write it as mv. So r is directly proportional to momentum of the particle. Higher the momentum of the particle, higher the radius, or higher the magnetic field, or higher the charge, lower the radius of the circle produced. And if omega is the angular frequency, then v equals omega r, angular frequency or angular velocity, where 2 pi is theta and v equals qb by m. Okay, from this we take omega times r equals velocity. So from the above equation, radius we will get velocity by r, which is equals to qb by m. and velocity by r, which is equals to angular frequency. So angular frequency, which is equals to qb by m. Or angular velocity, which is equals to qb by m. And this angular frequency independent of velocity or energy. Here v is the frequency of rotation, this is omega here. The independence of v from energy has important application in the design of a cyclotron. This angular frequency is independent of in energy of the particle. So this is an important principle in application of a design of a cyclotron, which will, I believe, you'll see later in this chapter. The time taken for one revolution is t equals 2 pi. Omega equals 1 by mu, I think. There is a component of velocity parallel to the magnetic field denoted by Vb. It will make a particle move along the field, and the path of the particle would be a helical one. The distance moved along the magnetic field in one rotation is called pitch. Using, we have pitch equals Vb is the velocity component, V cos theta, that is along the magnetic field direction, is equals to, we take it as where time period which is equals to 2 pi into mass Vb by qb. Okay, where they took time period equals 2 pi m by qb. 2 pi m by qb is equals to time period, and omega equals 2 pi by time period, which is equals to time period equals 2 pi by omega. So we know that omega equals qb by m. So we substitute omega here and we will get angular frequency here. We get that 2 pi m by qb is the time period, and velocity equals displacement by time, and velocity times time, which is equals to displacement. So based on these two formulas, we get that for a helical path, the distance, the pitch, or the pitch of the, or they said pitch meaning the distance moved along the magnetic field, where pitch is the, where pitch is the distance moved along a magnetic field. So this pitch we can write it as displacement, where pitch denoted by p, which is equals to the velocity component along the I mean along the magnetic field direction, or we can write it as V cos theta component times the time period. We can write time period as Vb times 2 pi mass by Qb, or 2 pi Vb times m by Qb. P equals 2 pi of Vb times mass by Qb. We can write this as a momentum along the magnetic field direction. This is the final equation they gave. The radius of the circular component of the motion is called as the radius of the helix. Now they give an example here. Example 4.3. What is the radius of the path of an electron? Mass is 9 to 10 power minus 31 kg, and the charge is 1.6 into 10 power minus 19, moving at a speed of 3 into 10 power 7 meter per second in a magnetic field of 6 into 10 power minus 4 Tesla perpendicular to it. They're asking if it is the velocity, the action of the velocity, and magnetic field is 90-degree. Then what is the radius of the circular motion? What is frequency? Calculate its energy, which is in kilo electron volt, or 1 electron volt is 1.6 into 10 power minus 19. Now based on R equals mv by qb for case 1 where theta equals 90-degree, we calculate, we will get that radius is around 28 into 10 power minus 2 meter, which is 28 centimeter, where velocity they took it as angular frequency, which is mu, I believe, is they took it as v by 2 pi r, which we will get it to be around 17 into 10 power 6 per second. We can write it as hertz, or 17 megahertz. And energy is half mv square. So mass of the electron is given, velocity is given, it is 40.5 into 10 power minus 17 joules, and in case of electron volts, we can write it as 2.5 kilo electron volt, which they wrote it as 4 into 10 power minus 16 joule, and they divided by 1.6. 1.6 into 10 power minus 19, we will get it 4 by 1.6 into 10 power 3, which is equals to 2.5 into 10 power 3 electron volt, which we can write as 2.5 into 2.5 kilo electron volt. Let's go to the next main topic, that is magnetic field due to a current element, that is the Biot-Savart's law. Let's see the illustration first. Figure illustration of the Biot-Savart's law. The current element I dl produces a field dB at a distance r. The x sign indicates that the field is perpendicular to the plane to this page and is directed into it. There's a wire that is having an arbitrary shape. The current is in this direction, and at a single element IDL, where we take a small element of the total length of the wire L as dl, then we take the r vector, which is a point at here in case of a point P, and point P here. In this case here, the direction of the magnetic field produced by this moving current, or the conductor, is a small magnetic field which is represented by dB, and it's perpendicular to the plane, and it is going into the book or into the screen. Okay, before and all we saw the effect of magnetic force and the like the magnetic force due to external magnetic force and the motion or the effect of this magnetic field and creation or interaction with the magnetic field and the particles or charges. Now we are seeing the magnetic field due to a current element. That is what we call it as Biot-Savart's law. All magnetic fields that we know are due to currents or moving charges. All the magnetic fields are due to currents or moving charges and due to intrinsic magnetic moments of particle. Here we shall study the relation between current and the magnetic field it produces. I think it's better if I continue this after a break of 10 to 15 minutes. Okay then. Okay, then it took a little more than 50 minutes, but fine. Let's continue. Okay, we were about the Biot-Savart's law. The magnetic field due to current element, that is Biot-Savart's law. All magnetic fields that we know are due to currents or moving charges and due to intrinsic magnetic moments of particles. Basically, all the magnetic fields are generated due to moving charges, that is currents, and that or other due to intrinsic magnetic moments of particles, like the spin of an electron, revolution of an electron, that kind of things. And here we shall study the relation between current, the moving charges, and the magnetic field it produces. And it is given by Biot-Savart's law. This figure shows a finite conductor XY carrying current I. Consider an infinitesimal element, a very small element, d of the conductor, dl of the conductor, the magnetic field dB due to this element to be determined at a point P, which is at a distance r from it. Let theta be the angle between dl and the displacement vector r. According to Biot-Savart's law, the magnitude of magnetic field dB is proportional to the current I, the element L, the length element L, and inversely proportional to the square of the distance. Its direction is perpendicular to the plane containing dl and dr. Thus, that is, in vector notation, we can write as dB is directly proportional to idl into r by r cube. It is inversely proportional to r square, but we take r above, so we write it as r cube down. And here we also take a sine theta because it is along this perpendicular to the plane containing, so it will be a sine theta as well. And the proportionality constant for dB equals proportionality constant k, which is equals to mu naught by 4 pi, where mu naught value is the permeability of air or free space. Permeability of free space, the value is 4 pi into 10 power minus 7. So final value is 10 power minus 7 of the k constant. This is the final equation where mu naught by 4 pi is the constant of proportionality. The above expression holds when the medium is in vacuum, as it is permeability of free space. The sense of dl times r is also given by the right hand screw rule. Look at the plane containing dl and r, where dl is the small length element and r is the position vector. Imagine moving from first vector toward the second vector. If the movement is anti-clockwise, resultant is towards you. If it is clockwise, resultant is away from you. Basically, they're telling about the right hand thumb rule, where we see the plane dl and r. Imagine moving from first vector to the second vector, from first vector to second vector. If the movement is anti-clockwise, then the resultant is towards you. If it is clockwise, then it is away from you. When we go from this way, from this vector to this vector, this motion we know is clockwise. So according to that, the resultant is away from us, like this way, or into the plane. In case if it is in this way, then the resultant is towards us. That's what they're saying. That is a screw rule. In case of the right hand thumb rule, the thumb will indicate the direction, where you curl your fingers from the first vector to the second vector. The thumb will indicate the direction. The magnitude of this magnetic field is the magnitude of dB, which is equals to mu naught by 4 pi idl sine theta by r square, where we have to use the property of cross product. Equation 4.7 into a, where they didn't write sine theta equals it because they wrote L cross R, so it is sine theta is already there, vector product. This above equation constitutes the basic equation for magnetic field. The proportionality constant in SI units has the exact value of 10 power minus 7 Tesla meter per ampere. That is a unit. We call mu naught the permeability of free space or vacuum. The Biot-Savart law for magnetic field has certain similarities as well as differences with the Coulomb's law for electrostatic field. Some of these are this one. It is somewhat similar to the Coulomb's law, that is the magnetic electric field which is equal to kq by r square. Here it is ideal sine theta by r square, k ideal sine theta by r square. Let's see the differences and similarities between these two laws, where F equals F electric, which is equals to k q1 q2 by r square, or Fp equals 1 by 4 pi epsilon naught. 4 pi is similar here, q1 q2 by r square. Electric field equals 1 by 4 pi epsilon naught q by r square. Both are long range, since both depend inversely on square of distance from the source to the point of interest. The principle of superposition applies to both fields. In this connection, note that the magnetic field is linear in source. Ideal is just the electrostatic field is linear in its source, the electric charge. Okay, the first information they gave it is both are long range because they depend inversely on the square of distance. That is the first information. Second information is the principle of superposition. Basically, if you want to find due to numerous electric field or numerous magnetic fields, the total magnetic field or net magnetic or net electric fields at a single point due to numerous magnetic or electric fields, we take individual vector sum of magnetic and electric fields to find the net magnetic and electric fields respectively. That is the principle of superposition. In this connection, note that the magnetic field is linear in source, that is ideal, just as electrostatic field. The magnetic field is linear in the source, ideal. Electrostatic field, electric field is linear in its source, the electric charge. Here the source of the magnetic field is the moving current per unit length element, just like how the electric field depends on the or linear to its source, the electric charge. I'm not sure what they mean by linear here. I believe it is dependence they are talking about. What does the above statement from NCERT mean? The principle of superposition applies to both fields in this connection. Note that the magnetic field is linear to its source, just as this refers to the principle of superposition and constant of electric and magnetic fields. The net field due to multiple sources is the vector sum of the fields due to sources individually. Okay, linear source, what that means is, okay, the field is directly linear in source, meaning the field is directly proportional to the source, where in case of electric field it is directly proportional to the charge, whereas the magnetic field it is directly proportional to the ideal, where it depends both on the current and the length of the small element. This linearity This is what allows us to apply superposition. We can just add the contributions from different sources. Both electric and magnetic fields obey the principle of superposition because they are linear in their sources, electric charge and current element respectively. So total field is the sum of fields from individual sources. Okay, then let's continue. The electrostatic field is produced by a scalar source, namely the electric charge. The magnetic field is produced by a vector source, that is IDL. The electrostatic field that is produced by a scalar source, but the magnetic field is produced by a vector source, that is IDL. Electrostatic field is is along the displacement vector joining the source and the field point. That the electrostatic field is along the displacement vector joining the source and the field point. Basically the position vector, it's along the position vector direction. The magnetic field is perpendicular to the plane containing the displacement vector and the current element IDL. Okay, in case of the electric field, it is in the same direction as the position vector, but in case of the magnetic field, it is perpendicular to the plane containing the displacement vector R. It is directly, if the R vector is in the xy plane, then the magnetic field will always be in the z axis, in the z line, or in the z axis. Basically it will always be perpendicular to the plane of the R vector. And also the current element, this is an angle dependence in the Biot-Savart law, which is not present in the electrostatic case. We see here sine theta, but in case of the Coulomb's law, there is no sine theta or cos theta here. There is no angle dependence here. But in case of the magnetic field, we have a angle dependence. There's an angle dependence in the Biot-Savart law. In figure 4.7, the magnetic field at any point in the direction of dl is 0. This is a 4.7 figure, and they said that a magnetic field at any point in direction of dl, any point, the direction of dl is, I believe, this direction, a tangent here. From here it is the r vector. At any point in the direction of the ideal, it will be 0. Maybe it's because it's perpendicular, or it is along the direction of magnetic field. In that, along this line, theta equals 0, sine theta equals 0, sine 0 equals 0, and from equation 4.78, the magnetic field is 0. They showed a dashed line, this is a dashed line, and in this direction the theta equals 0. I dl, so L into R, L cross R. Okay, let's continue. There is an interesting relation between epsilon naught, the permittivity of free space, and mu naught, the permeability of free space, and c, the speed of light in a vacuum. Epsilon naught mu naught is equals to 4 pi epsilon naught mu naught by 4 pi. Okay, they introduced 4 pi, they multiplied 4 pi and divided by 4 pi, and we know that 1 by 4 pi epsilon naught is equals to 9 into 10 power 9. So 4 pi epsilon naught we can write it as 9 into 10 power 9, and mu naught by 4 pi we can write it as 10 power minus 7, and this is actually 3 into 10 power 8 whole square, which is the approximate speed of light in a vacuum. So in free space, if we consider when we multiply epsilon naught and mu naught, we will get that it will be equal to the inverse of the square of speed of light in a vacuum, or we can say c equals a root of 1 by epsilon naught mu naught. We will discuss this connection further in chapter 8 on the electromagnetic waves. The speed of light in a vacuum is constant. The product mu naught epsilon naught is a fixed magnitude. Choosing the value of either epsilon naught or mu naught fixes the value of any kind of mu naught or epsilon naught we take. The other value will be fixed, as it will be equal to 1 by c square. In SI units, mu naught is fixed to be equal to 4 pi into 10 power minus 7 magnitude. Okay, there's an example here. An element delta L, which is equals to delta X I cap, is placed at origin and carries a large current of I equals 10 ampere. What is the magnitude field on the y-axis at a distance of 0.5 meter? Delta X equals 1 centimeter. The given information is that the length equals delta X I cap. It is placed at the origin. The current to be equal to 10 ampere, and they give angle is 90 degree because it is in the y-axis. Distance is 0.5. So direct formula, dB equals mu naught by 4 pi IDL sine theta by r square. Delta X equals 1 centimeter, which we can write as 10 power minus 2 meter. I equals 10 ampere. R equals 0.5 meter, which equals to y, and sine 90 degree equals 1. So dB equals 4 into 10 power minus 8 Tesla. The direction of the field. The direction of the field is in the plus z direction. This is so since dl times r is equals to delta I cap times y cap is equals to y delta x, which is I cap times j cap, or cross product of I cap into j cap, which is, we know it is k cap. We remind the following cyclic properties of cross product, where I cap times j cap is k cap, j cap times k cap is I cap, and k cap times I cap is j cap, where I cap times I cap, or j cap times k cap, j cap, or k cap times k cap will always be 0, because sine 0 will be 0. And this field is in small magnitude. It's in 10 power minus 8 Tesla, or 40 nanotesla. In the next section, we shall use Biot-Savart's law to calculate the magnetic field due to a circular loop. Magnetic field on the axis of a circular current carrying loop. This is, let's see the diagram first. There is a circular loop that is carrying a current here like this, and this is the center of the loop. They showed the axis here. There's a small displacement here. If we take small displacement dl, and this is the r vector, this is the distance from the center, this is a point P, this is the r vector to the point P from the small displacement dl, x is the distance from the center, and this is the radius of the circular loop, and the magnetic field, the direction of the magnetic field will be perpendicular to both the r vector and the magnetic, it will be perpendicular to the r vector, so it will be in this direction. This is the perpendicular sign component of the magnetic field. This is the cos component, which is dbx. In this section, let's see the diagram. Magnetic field on the axis of the current carrying loop of radius r. Shown are the magnetic field dB due to a line element dl and its component along and perpendicular to the axis. In this section, we shall evaluate the magnetic field due to a circular coil along its axis. The evaluation entails summing up the effect of infinitesimal current elements IDL mentioned in the previous section. We assume that the current I is steady and that the evaluation is carried out in free space, that is vacuum. Figure 4.9 depicts a circular loop carrying a steady current I. The loop is placed in the xy plane with its center at the origin and has a radius r. The x-axis is the axis of the loop. We wish to calculate the magnetic field at the point P on the axis. Let x be the distance of P from the center of the loop. Basically, they're saying whatever I said before is just depicting the figure. They're saying that magnetic field due to a circular coil along its axis. That is what we are evaluating. And this evaluation entails summing up the effect of, we sum up different small current magnetic fields due to small current elements. We add them all up to get the net magnetic field at that point at the axis. And this figure depicts a circular loop carrying a steady current I. It's a steady, non-varying current, and this loop is placed in the xz plane, with x-axis is the axis of the loop. We wish to calculate the magnetic field at a point P on this axis, and let x be the distance of P from center of the loop. Consider a conducting element dl of the loop. This shown in the figure. The magnitude of dB of the magnetic field due to dl is given by the Biot-Savart's law, which is dB equals u0 by 4 pi I dl times r, or cross product with r by r cube. Now r square is equals to x square plus r square based on the Pythagorean theorem. Further, any element of the loop will be perpendicular to the displacement vector from the element of the actual point. Okay. They're saying any element of the loop will be perpendicular to the displacement vector from the element of the axial point. This is the displacement vector. This is the dl. Fine. For example, the element dl in figure 4.9 is in the xy plane, whereas the displacement vector r from dl, the actual point P, is in the xy plane. Hence, dl times r, which is equal to r dl, r and the dl basically, okay, this here, both will be perpendicular. So in such a case, sin 90 equals 1. So we can write dl times r as simply r dl, and in such a case, we can write it like, if we write it like that, mu naught by 4 pi r dl by r cube, for r square times r cancel, mu naught dl by r square, mu naught by 4 pi dl by r square will get, and we know that r square equals x square plus r square, capital R square. This is based on the Pythagoras theorem, and we will get dB equals mu naught by 4 pi I dl by x square plus r square. The direction of dB is shown in figure 4.9. It is perpendicular to the plane formed by dl and r. It has an x component dbx and a component perpendicular to x-axis, dby or dp perpendicular. The components perpendicular to the x-axis are summed over, they cancel out, and we obtain a null result. For example, the dB component due to dl is cancelled by a contribution due to the diametrically opposite dl element shown in the figure. Thus, only the x component survives. The net contribution along the x direction can be obtained by integrating dbx, which is equal to db cos theta, over the loop. Okay, since the db is along this direction, and when we resolute this db vector, we will get db in the y direction and the x direction, or the sine and cos components. In this case, this will get cancelled out, because if we take this element in case here, then we will get a direction db in this direction, so they both cancel out. So the only thing that remains will be in the dbx direction. So we only need to calculate the dbx. That is what they're saying here, and we can take dbx equals db cos theta, and based on this we can integrate this. We will get the total magnetic field, where cos theta equals base by hypotenuse or adjacent by hypotenuse, and based on this, base is the radius, hypotenuse is the root of x square plus r square of, or yes, basically that itself. From equations 4.9 and 4.10, dbx, in this formula we substitute mu naught I dl 4 pi r by x square plus r square 3 by 2 Okay, based on this equation where dbx equals db cos theta, we know the value of db, which is mu naught 4 pi idl by x square plus r square, that we substituted here, and we know that cos theta value from this equation, cos theta, we will get it as r by x square plus r square by 1 by 2, and we have x square plus r square whole square times of root of x square plus r square. We will get x square plus r square whole 3 by 2. This is the final dbx. Now summation of elements dl over the loop yields 2 pi r. So circumference of the loop, thus the magnitude at p to entire circle or loop is b equals bx I cap mu naught I r square by 2 x square plus r square whole 3 by 2, whole power 3 by 2. Basically, we are integrating this, and the constants are, we know mu naught is constant, 4 pi is constant, I is constant, and radius is also constant. And basically everything is constant here. Only remaining thing will be constant differentiation of dl should get to be L 0 to 2 pi r, the circumference. Then we will get the final value to be, if we substitute this with the constant, we will get mu naught I r square by 2x square plus r square whole 3 by 2 I cap. A special case of the above result, we may obtain the field at the center of the loop, where x will be equal to 0. If we substitute x will be equal to 0, then we will get mu naught I r square by 2r square, r square get cancelled, and we will have 1 r here, as there is a power 3 by 2 here. We will get b naught equals mu naught I by 2r magnitude of field lines due to a circular wire form closed loops and are shown in figure 4.10. The magnetic field lines for a current loop, the direction of the field is given by the right hand thumb rule described in the text. The upper side of the loop may be thought as the north pole and the lower side as the south pole of a magnet. This is a loop where the current is going from here to here. In this case, when we apply the right hand thumb rule, you'll get the direction to be like this, which we'll read, and they will be coming back like this. So this is the south pole, this is the north pole of a bar magnet, where inside the loop the magnetic field lines are going from south to north, but outside they are going from north to south. The direction of the magnetic field is given by another right hand thumb rule stated below. Curl the palm of your right hand around the circular wire while the fingers pointing in the direction of the current. The right hand thumb gives the direction of the magnetic field. When we curl our fingers in the direction of the loop, that is in the direction of current flowing in the loop, then the thumb will point the direction of the magnetic field. Okay, there is an example given here. A straight wire carrying a current of 12 ampere is bent into a semicircular arc of radius 2 cm as shown in figure 4.11. Consider the magnetic field B at the center of the arc. Okay, they are saying a straight wire carrying a current of 12 ampere is bent into a semicircular arc having a radius of 2 cm as shown in the figure. Then A, what is the magnitude, what is the magnetic field due to the straight segments? There are straight segments. What is the magnetic field due to them? In what way the contribution to magnetic field from semicircles differ from that of circular loop, and in what way does it resemble? C, would your answer be different if the wires were bent into a semicircular arc of the same radius but in the opposite way as shown? Okay, they gave information that it's a straight wire carrying a current 12 ampere, or it is bent into a semicircle. This is the diagram. This is the only diagram. For C question, they just changed diagram. It is semicircular arc that is having a radius 2 cm. Now the first question is, if there is a magnetic field at the center of the arc, that is B, then what is the magnetic field due to the straight segments? Will there be a magnetic field due to the straight segment? In what way the contribution to magnetic field from semicircle differs from that of a circular loop, and in what way does it resemble? This question, because it is not a circular loop, in this case the sign components do not get cancelled here. The sign components do not get cancelled, and in case of resemblance, if we say, the cos components do get added up. That is a resemblance, but the sign components do not get cancelled in case of a semicircular arc. Okay, let's see the solution. For first question, what is the magnetic field due to straight segments? dl and r for each element of straight segments are parallel, therefore dl times r, which is equal to 0. Straight segments do not contribute to the magnetic field. dl and r, basically the small length element and the position vector. If we take at the center here, these vectors are parallel here. So in this case, sine 0, which is equals to 0, so the straight segment do not contribute to the magnetic field B. For all segments of semicircular arc, dl times r are all parallel to each other into the plane of paper. All such contributions add up in magnitude, hence direction is for B for semicircular arc is given by the right hand rule, and the magnitude is half that of the circular loop. Thus B is 1.9 into 10 power minus 4 Tesla, normal to the plane of the paper going into it. Here the direction will be normal to the plane of paper. Same magnitude of B but opposite in direction to that. In this case, for this diagram as well, same in magnitude but direction will be opposite. Now let's consider a next example is consider a tightly wound 100-turn coil of radius 10 centimeter carrying a current of 1 ampere. What is the magnitude of the magnetic field at the center of the coil? There is a coil that is having a radius of 10 centimeter. It is wounded into 100 turns. It's carrying a current of 1 ampere. What is the magnitude of magnetic field at the center of the coil? We know the magnitude at the center of a coil of a circular current carrying loop will be mu naught I by 2r. But in this case, when there are tightly wounded, we introduce n, which is the number of turns, which is 100. So mu naught by 2r into 100, which gives us the total magnetic field, which if we put the values here, we will get it to be around 2 pi into 10 power minus 4, which if we substitute 3.14 as the value, we will get 6.28 into 10 power minus 4 Tesla. The total magnetic field due to 100-turn coil of radius 10 centimeter that is carrying a current of 1 ampere. That is it for the examples under the Biot-Savart law and circular loop. I will continue the Ampere circular law in the next video, hopefully. Then